All right, so let's go on to page 2. And we're going to continue the idea of looking at a function in order to graph it. And there may be some tricks and strategies that you remember from middle school. Those are great strategies. Use them. Rest in the fact that you know how to graph based upon, well, for example, example 3, this is the y-intercept and this is the rate of change. So if you yada yada, step 1, step 2, step 3, you'll find the picture of the line. And those are great. I want to use those, and I'll sneak into using those results or tricks. But when you're stuck and the function is not a nice linear function, at the very least, do what we're going to do in example 3 every time. We'll use Desmos, so you can still see that I've got those functions from Desmos from the previous one up there. I'm going to go ahead and just clear it all out. We use Desmos in order to graph the functions we're given. And there's some features of Desmos that I want you to know about too that'll kind of make some of the work you have to do faster, but it's always good to do some of the stuff by hand. Okay, in example 3, consider f of x equals negative 1/3 x plus 6. Complete the table to represent functions. I read it wrong. Complete the table to represent solutions to f of x. A solution is an ordered pair, x and y, and when you plug in your x number, the y value you get back goes with that number. So together they make what we call a solution. And technically, the line that's graphed is all of the solutions, every infinitely many possible number of solutions to that function. So here with this table, we hope to get a good idea of what all those functions, all those solutions look like by graphing, or by first of all finding if x is negative 6, what's f of x, and then do that for these 5 values, and then use those to kind of predict what the shape of the function looks like so that all of the solutions of the function follow that pattern. It's going to come down to plug and chug. So what I mean is, if our first number in the first cell, x is negative 6, then that means our function notation as f of x, we're going to change the x to the number negative 6. And so everywhere in the equation, the x becomes that number. Negative 1/3. Aha, there's an x, but we're using for the first time ever the negative 6 that's there. And plus 6. And then we just simplify this math to get an answer. In my head, I would do the negatives. That makes it positive. 1/3 of 6 is 2. 2 plus 6 is 8. So I'm going to put in 8 right there. That is the concept of doing it by hand. I'll do one more, and then I'm going to use Desmos because, come on, we have technology. So the next one over. Actually, I think you can do the negative 3 and the 0. I want to jump to the answer, this y equals 2. Remember, y equals f of x. Not that they're, directly equal, but that they're close enough that we just swap notation with them. Oh, time for me to show you my smarts. F of x comes from my favorite mathematician of all time. This is notation that was, I'm going to credit Euler for the guy that invented it, but if he didn't invent it, he certainly made it a thing. So Leonard Euler. It looks like Euler, but it's not. It's oi, like eh boy. Okay, so we have y as the f of x from the function. So we're really saying that y equals f of 2? No, we're saying that this is f of x. And then that means that 2, because up here, f of x is the answer, these are the answers, and we're going to put these numbers on the outside. This isn't evaluating a function, this is solving for x in a function. We write the rest of the problem that's there. Negative 1/3 x plus 6. Okay, algebra time, solve for x. Minus 6 minus 6, negative 4 equals negative 1/3 x. The 6 is gone. Times by negative 3, because that's the reciprocal of the coefficient of x. Multiply by negative 3 to both sides, and you get 12. Let's prove it. Yeah, let's prove it. Okay, so first of all, I'm going to go to Desmos. I'm going to type in f of x equals. And the reason for the f of x is Desmos is able, like you saw in the previous video, on the previous page, when you write f of x into Desmos, it's able to think about what you're doing as a function and then do all these awesome, wacky, fun things that we have access to now. Okay, I'm gonna get that out of the way for a second. I mean, it's a line, right? We have a line. We're gonna graph a line in the space, but in order to do that, it'd be really helpful to. Yeah, whew, I had a heart attack for a second there. I looked at my 12 and was like, that's wrong. It's not. Okay, here's where the Desmos is really, really cool, and also where it helps us take some shortcuts, because doing, this stuff by hand is redundant. I'm going to make you do it anyway, though. Okay, so table. Whoa, I'm sorry, you didn't see what I did there. First of all, when you click the little gear on the row where you're entering your rule for your function in Desmos, that little gear, settings, you can change the color of the line if you wanted to. You could change its texture, whatever it was. It's a continuous line. You need to draw a straight line, so keep it solid. But the other thing that's really cool about the table is that the gear is that this little table icon pops up, and what's all of the times that you need to know the actual points? I mean, look, -2, -1, 0, 1, 2, they all are plotted visibly as dots on the graph that's there, and you can use them. So I guess the 0, 6, that's what I'm going to write right here. Okay, I'm seeing this table is useless. It has none of the numbers from my other thing. I wonder if I can just delete. Oh my goodness. I mean, I already knew that. If I put a 12 there, 2, answer, check 1, check 2. 0 makes a 6, -3 makes a 7. Okay, here we go. Here we go. Now I got to get to a 0 in this column. This is the f of x column. That's the 0 that's waiting right there. I could solve for it. I was going to go 13, no. 14, no. 15, no. 18, yes. I guess it kind of makes sense. -3 times 18 is -6. -6 plus 6 is 0. So that fits, logically how things are supposed to go. Now, taking these points. So we have these points right here. We need to plot them in a table. And this is where I'm going to remind you of tails plus. I heard it from a math guy that teaches like in Leavenworth, and I'm like, that's genius. And so I'm going to try to emphasize it as much as possible here, and then hopefully it sticks in your brain for the rest of your life. All right, start off with a title. There's no need for a title. It's no context. But I know that I'm kind of using Desmos. I kind of see this, centered around the origin. I know that I'm going to go from like -6 to 18. Uh-oh. Okay, ignore this line right here. I want to have 18 points. Maybe I'm going to go by 3s. That's already talking about my scale. Title, axis, interval, labels, scale, and your graph should go through, or the line you're drawing should go through about 50% of the space. Like, it shouldn't be up here in the corner or down here in the other corner. It should go roughly through the middle. That's what the plus represents. Go through roughly 50%. I think I'm gonna make a switch here. And I'm going to put my x-axis right there. I mean, that's not my x-axis, that's my y-axis. My bad. And then I'm looking at Desmos and realizing that most of the graph is above the x-axis for quite a ways. I mean, it's not until almost like 20 when it finally crosses below. So that means I'm probably going to put my x-axis for real. If you can kind of see it, 5 spaces up, right about here. I'll highlight it if I have to. Okay, x and y. So there I'm labeling my axes. My interval, I mean, I'm going to use my table. I have to go from -6 to 18. I have to go from 8 to 0. So I'm not actually going to use the squares of the boxes. And you can choose whatever whatever scale that you want. But I think I'm going to go by 2s on the bottom. So 2, 4, 6. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And I could have done it. Oh well. 2, 4, 6, 8, 10. Okay. It is what it is. And then I'm going to go by skipping. So 2, 4, 6, 8, 10. 2, 4. -2. Am I doing that right? I'm not doing that right. 1, 2, 3, 4, 5. 6, 7, 8. Nope. I'm going by 1s. Yep, just rolling with the flow. So in case you were wondering, I'm going 2, 4, 6, 8, but I'm going -2, -4, 2, 4, 6, 8. I mean, it's enough to try to fit in the weird space that's there. Don't think that you have to go 1 square, 1 space, 1 square, 1 space all the time. As long as you go consistently along that axis and consistently along this axis. Okay, plotting them. -6 and 8, -3 and 7, 0 and 6. This should be enough to draw the rest of the line, but I'm going to continue out plotting all these points. 12 and 2 and 18 and 0. And with a smooth curve, there we go. Okay, the last part is to label. So somewhere along this line, I'm going to put f of x equals -1/3 x plus 6. All right? Okay, moving on to the next question. Exercise 4. Sorry, I'll try to keep it simpler. I can't. This question's, a good question. A lab researcher records the growth of the population of a yeast colony and finds that the population doubles every hour. Complete the researcher's table of data. So at 0, there's 5,000 bacteria. 1 hour later, there's 10,000 bacteria, and then 20, and then 40, and then 80,000 bacteria. Keep in mind the thousands right there. This actually does work as a formula. I mean, all you had to do is guess and check. Desmos, get rid of this, get rid of this. Let's go. Desmos doesn't like y's and t's to graph. I mean, it can handle it, but if you want to actually see a picture of it, you need to use f of x, which means all of your y's and t's turn into, like, t is x and f of whatever is the y part. So it's not visible. Oh, there it is. Yep. Okay. Does this work as a graph? If I click the table, I don't need that. That's 5. 1, 2, 3, 4. Yeah, there you go. My table from Desmos matches my table that I just calculated. So this function, 5 times 2 to the x, that works. Some of you were stuck on that question on the on the quiz that we took, and I'm telling you, like, plug it in. Well, several hours into the study, the researcher looks at the data and wishes there were more frequent measurements. Knowing that the colony doubles every hour, how can the researcher determine the population in half-hour increments? Plug them in. But don't think that it splits the difference, right? If you split the difference here, this is not 7.5. No. It's an exponential function. From 1 to 2, halfway between at 1.5, it is not 15. That'd be a linear situation. Exponentials are not linear. There's some sort of multiplication factor that you have to keep in mind. Nope, and nope, and nope. It's not exactly in between 20 and 40. I mean, just go back to Desmos. Turn the page and take a look at that. I mean, we already know that 1 is 10, 2 is 20, 3 is 40, I almost said 30. And in Desmos, don't do that. In Desmos, if we type 0.5 here, 7.071. Let's round to hundreds. Hundreds are easier to write down. Okay, 3.5, 1.5, I guess. 14. It seems like the closer, what if I go 1.7? That's closer to the middle. So if I shift closer to the 2, I get closer to the halfway point. Exponential functions are about multiplying. So there is a multiplicative middle between two intervals, not necessarily like an add up rate of change. It's a scale factor, a multiply factor. I want 1.5, by the way. So 14.14. Okay, now we're up to 2, and then if I need more space on Desmos, I'll just go down the line, go 2.5. 28. Oh, weird. It's like twice of this. This doubles to 14.14. Did you see that? And then the 14.14 doubles to 28.28. So it's like there's doubling here, because those are all doubling by an hour, but there's also doubling here, because these are growing by an hour increment. That's a light bulb moment for me, actually. I hadn't really thought of it that way, but thinking about it, I mean, it makes sense to me that you're doubling, your hours are increasing regularly. So whatever hour increment you're stopping on, as long as you go an hour later, you have twice as much. That's the function. Okay, let's plot it. Tails plus. I mean, you don't have to really write the tails plus. You can do what I do if you want. But the purpose of the tails plus is to remind me I need a title. It's time for a title. Yeast population over time. I ran out of room on my title space. You should try to fit it better. Or don't. Write in pen like I do. Yay. Okay. Our axes, this is time, and this is yeast population. So yeast y of t. Our interval for hours of study, I guess because I go to 3 right here, I'm going to go, this is 1, 2, 3, 4. I mean, I could bring in the table from here and go up to 80. So from 0 to 40, 0 to 4, and then 1, 2, 3, 4, 5, 10, 15. 80 divided by 15. 80 divided by 16. My brain just broke. Let's go by tens. Let's go that every 2 spaces is 10. So here's 10, 20, 30, 40, 50, 60, 70, 80. Yeah, that's what I meant to do all along. Okay, so from 0 to 80 going by 1, 2, 3, 10, 20, 30, 40, 50, 60, 70. Okay, so title. Our axes are labeled. Our interval is chosen. We have scaled accurately. And because of the way that we scaled it, our graph should go through the middle 50%. So now it's time to plot it. 0, 5 here. A half is 7.071. 1 is 10. I'm going to do the integers first. 2 is 20. 3 is 40. Okay, and 4 is 80. And then I'm going to fill in these other pieces. So 1.5 is 14.14, so just a shade under. And 5 halves is 28.28, so just a shade under 30. I mean, you can see right there, they start to fit that smooth curve. And if we click the wrench in Desmos and do the same thing, 0 to 4. So my x-axis going by ones, this is t. Didn't you know you can do that? Our y-axis goes from 0 to 80, going by tens. Let's go fives. Going by fives, and sure, arrows, why not? Okay, I'm gonna get rid of that picture there. There it is, smooth curve. Now I've got a little more like spread out. I mean, if I kind of drag this to make it steeper, you kind of see a little bit better of what's going on. But yeah, there it is. We're just messing with the axes themselves. So smooth curve through these points. I'm going to use Desmos for a second. I want to find 3.5. 3.5. 56.5. Yeah, double 28, 28. 56.56. So 56.6. Okay, just enough to kind of see some of the pattern between here. Smooth curve. Draw a smooth curve through the points. And kind of nailed it, so I'll count it. All right, I'm going to use an arrow on this end because, as the population continues to grow, I mean, as bacteria continues to multiply, as time marches on, you'll have more and more and more. But I'm not going to put an arrow on the other side because there's kind of like an initial value. It's like it started right there. And there you go. Explain what the y-intercept represents for bacteria growth. I mean, when the experiment... when the research started, there were 5,000 bacteria. Okay. Oh, sorry. All right. I strongly recommend that you do exercise 5, only because I'm running out of time. Homework. It's for you. You know who you are. You have to do this one. Okay. I'm checking the next page. Yes. Okay. So let's go ahead and take a look at exercise 6. And exercise 5, you need to do that one. You should be able to do that one. All right. Use the table or use the graph of k of x to complete the table. So literally just marching along the space trying to find values. When x equals -8, k of x equals, I guess I should say k of negative 8. K of negative 8 equals 3. When x equals negative 4, k of negative 4 equals 8. Okay, you don't actually have to write these things, but I think it's helpful to at least get that duality there, that you have an x input and you have a k of x output. Okay, 0 is 5. And I think they want to continue us going this way, but if we see a 1, like 1 is right here, so negative 9 is a possible answer, but it doesn't kind of fit the flow of the column, so maybe negative 9 is not the number you want to use. Oh, lies, it has to be that one. How about 8? So 8 happens at negative 2 and at negative 4 and again at 9. So pick your favorite one for those 3 that remain. I guess I'd kind of like to have 9. Positive numbers, right? Okay, use the graph y equals k of x from the previous, from above, to evaluate the function. If x equals 0, then k of 0 is the height location on the graph where the x coordinate is 0. So k of 0 equals 5. What is k of 2? 5. What is k of negative 1? 7. When k of x equals 3, identify the x distance on the graph where the function k has a height of 3. Whew. I mean, I wrote that, so sorry that you had to deal with it. But what I'm really answering is when the height of the function is 3, the x location is negative 8. It's really just trying to show you that this is distance on a graph. So your 3 spaces up and that way, whatever the direction, that way, right? You go to the left negative 8 spaces in order to find this point right here. It's on the function. So a solution would be the ordered pair negative 8, 3. That's a solution, and there are many. For what x values does k of x equals 0? We're going to guesstimate that negative 10 is that point. So x equals negative 10. And where does k of x equal 5? Here, and here, and here, and here, and here. So that'd be 7, and 5, and 2, and 0, and negative. There's a lot of places where the function has a height of 5. Those all have the same height, but they occur in different x values. That's still okay. It's still a function. Vertical line test continues to work, but there are several x choices. So fill in whatever your favorite one is or fill in all of them. On what intervals does k of x increase the fastest? Great question. Easy answer. Look for the steepest section of the line. It looks like this line is increasing, but this section's increasing steeper at a rate of about 2 to 1, 2 to 1. So that's pretty good. That's a 1-to-1 steepness. Nope, 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 nope. Maybe right here. Okay. That interval and that interval. Let's use inequalities to point it out. On what intervals do k of x increase? No, it is. On what intervals does k of x increase the fastest? So it increases from negative 9 to negative 7. Negative 9 is less than or equal to x is less than or equal to negative 7. And 8 to 9. 8 is less than equal to x is less than or equal to 9. Draw an arrow pointing to the y-intercept of the function. Boom, right there. Label it, I guess, y-intercept. Okay. Looking on the next page. Please do the closing. Think about it. Ponder, understand, and assess. The exit ticket might be a quiz question coming up in the future. It certainly is based upon Smarter Balanced items. And do the problem set. Oh, pretty fond of this. Okay, do the problem set for homework. Thank you so much. Have a good day. I'll see you tomorrow.